Japan's leadership in supercomputing has been revived. In November 2010, the Tokyo Institute of Technology, Tokyo Tech, developed and deployed the first-ever multi-petaflop supercomputer in Japan. 3 years later, Tsubame2 was upgraded as Tsubame 2.5 with overwhelming advances in computational performance. Tsubame stands for the Tokyo Tech supercomputer and ubiquitously accessible mass storage environment. Tsubame in Japanese is a swallow, which is also a symbol of our university.
In 2006, we developed a supercomputer called Tsubame2. According to the top 500 list, Tsubame2 was ranked 4 consecutive times as the fastest supercomputer in Japan and achieved unprecedented 7 consecutive performance improvements, literally symbolizing Tokyo Tech with its continuous evolution over the years.
In 2010, a new version of Tsubame, Tsubame 2.0, was developed as the first petascale supercomputer in Japan, and now upgraded as Tsubame 2.5 in 2013 with overwhelming advances in computational performance. This is the result of global collaborative design and development with world-renowned vendors partnering with Tokyo Tech to offer the latest technologies in supercomputing. Tsubame2 combines scalar processing of industry-standard CPUs with vector processing of industry-leading GPUs in a hybrid architecture, especially tailored to large-scale supercomputing. A total of 1,442 computing nodes achieve 5.7 petaflops peak performance, or 5,700 trillion floating point calculations per second, one of the world's top computing capabilities. This is a speed up of about 70 times compared to Tsubame 1 in 7.5 years. In single precision floating point arithmetic, Tsubame 2.5 exhibits 17.1 petaflops, making it the fastest supercomputer in Japan under that metric.
Tsubame2 is not merely an array of compute nodes equipped with high-performance GPUs. Supercomputers are designed with high bandwidth memory and high-speed network interconnects in order to efficiently deliver data to the processors. Tsubame1 exhibited only 17 terabytes per second of effective aggregated memory bandwidth, while Tsubame2 exhibits over 1.1 petabytes a second, an improvement factor of over 60. Each compute node is connected to a high-speed optical network that is 80 times faster than gigabit Ethernet on high-end PCs. The entire Tsubame2 network utilizes one of the world's fastest so-called full bisection optical networks, whose performance at 200 terabits a second allows all nodes to communicate simultaneously without congestion. The combination of all these architectural elements completes Tsubame2, which exceeds 2 petaflops per second peak performance.
Massive storage with extreme high-speed access is also very important. Tsubame2's hierarchical storage capacity is over 11 petabytes, or more than 10 times that of Tsubame1.
The primary level is a total of 119 terabytes of SSDs embedded in computing nodes as scratch spaces, providing ultra-fast 2/3 terabyte per second I/O bandwidth. The secondary level is the 6 petabytes of parallel file systems such as raster, GPFS, allowing extremely fast access to petabyte scale data. In addition to the 1.2 petabyte of home storage for providing campus cloud services as everyone's supercomputer. The tertiary level is 4 petabytes of tape library storage, bringing the total storage capacity is up to 11 petabytes, making Tsubame largest storage capacity in all Japanese supercomputer centers.
Immense scaling and the complexity of modern-day supercomputers today pose not only high administrative costs, but also a tremendous carbon footprint due to significant power consumption. Tsubame2 is employing various technologies to become the smallest and greenest petascale supercomputer in the world.
Tsubame2 is already highly attractive due to its petascale computational performance. Additionally, the high computational power of GPUs allows for extremely high density in its packaging. Tsubame2 occupies only 2/3 of the footprint of Tsubame1. As for power consumption, compared to Tsubame1, which consumed approximately 1 megawatt under normal operation, Tsubame 2.5's power consumption is even lower despite the factor 70 performance boost. In addition, we employ the latest rack-contained water cooling system with a built-in heat exchanger, allowing the high-density racks to be cooled effectively with completely automated control to minimize power consumption. As a result of these efforts, Tsubame2 received extremely high accolade in its power efficiency, being given the greenest production supercomputer in the world special award on the Green 500 list. This was announced at the SC10 conference in November 2010, the largest supercomputing conference in the world. With the 2.5 upgrade, we expect Tsubame to be competitive again for the SC13 announcement of the Green 500 list.
In addition to adopting low-power architecture, we focus on power saving in daily operation of Tsubame. Power saving of supercomputers is highly important, especially after the Great East Japan earthquake. First, we started operation of a new visualization system of power consumption of Tsubame. Now, Tsubame is a rare supercomputer that makes its real-time power consumption open. Recently, as a social demand in Japan, we are requested to save the power, especially in summer. For this demand, we developed and started a new power control system that automatically controls the number of working computer nodes in the daytime in summer.
Not only for the current supercomputers, but we are promoting research to make next-gen supercomputers even low power. For this purpose, we are developing container-based research facility named Tsubame KFC. In Tsubame KFC, we introduced a new liquid submersion cooling method, where the entire compute nodes are submerged in the coolant liquid. Additionally, we use outdoor air cooling to keep the temperature of coolant. By combining these technologies, we aim at making Tsubame KFC one of the most power-efficient systems in the world.
Tsubame 2.5 will be the first Japanese system to achieve world top-class multi-petaflops performance. Let's look at the applications that will exploit the possibilities of such unprecedented performance.
Tsubame is definitely a world top-class supercomputer. The most important is to make great contributions to science and engineering. For this purpose, users occasionally have to learn GPU computing or CUDA programming. We have been studying large-scale stencil applications. In 2011, our team received the Gold Bell Prize, and we showed Tsubame is really available for practical applications. Using doubly powered Tsubame 2.5, a lot of results were strongly expected.
The alloy materials are used everywhere in the world. The mechanical properties of these materials largely depend on their internal microstructures, including dendritic growth observed in solidification processes. To develop engineering materials with the expected properties, such as lightweight materials, predicting pattern in solidified metals would be indispensable. By using 4,000 GPUs on Tsubame efficiently with a novel computational method, we have achieved petascale high-performance computing for the solidification simulations. The ACM Golden Bell Prize was awarded to us in 2011 for this achievement.
A lot of tall buildings and complex structures make the airflow turbulent in large urban areas. In order to understand the detail of airflow in such areas, it is necessary to carry out large-scale CFD simulations. We used 4032 GPUs for computation on a 10 km square urban area of Tokyo with a 1 meter resolution. By executing this large-scale computation, detail of the wind behind the building and typhoon damage were revealed with much higher accuracy than ever before.
We have to reproduce the seismic wave propagation through the heterogeneous Earth in order to predict the strong ground motions due to earthquakes and to study the physical mechanisms of earthquake sources. Thus, we have been studying computational methods for the simulation of the seismic wave propagation through the Earth model. Now, high-performance, large-scale simulations are possible using the computing power provided by the Tsubame GPU supercomputer.
DNA sequencing technique is revolutionary changing, and the metagenome analysis of thousands of species in the environment can be rapidly analyzed. To support large-scale functional genome analysis, we need the power of Tsubame 2.5 with multi-node GPUs. Systematic protein-protein docking study for drug target discovery is also powered by Tsubame.
Tsubame 2.5 achieved speed up in many applications compared to Tsubame 2.0. Tsubame, as everybody's supercomputer, will further reach out for collaborations and services across Japan with its petascale capabilities. Our industrial usage program so far has accepted 145 applications from the private sector in order to disseminate the cutting-edge technologies in Tsubame 2.5. Such an effort has been rewarded with the highest review ranking from the Japanese government. In September 2012, we started HPCI, the Japanese high-performance computing infrastructure led by the ministry MEXT, with other supercomputing centers and national universities and laboratories across Japan, hosting bleeding-edge capability computing applications.
We have developed software package for large-scale mathematical optimization problems and graph analysis on Tsubame supercomputer. We have solved the largest mathematical optimization problem, which has over 2 million constraints, thereby creating a new world record. Our implementation also achieved 1.7 petaflops using the 4080 GPUs of Tsubame. We will have high expectations for the fast computation and high scalability of Tsubame.
We have been using the partnership resource allocations and grand challenge of large-scale GPU applications to analyze biological phenomena through molecular dynamics simulations and fluid dynamics simulations by the vortex method. We have succeeded in effectively using more than 4,000 GPUs in Tsubame for these calculations by implementing the fast merge pool method. Furthermore, we have achieved an immense acceleration in the most important and time-consuming Coulomb force calculations for molecular dynamics simulation and improved the parallelization of the fluid dynamics calculations by vortex method in comparison to previous used spectral method, which is based on FFT. We expected to be able to produce more research results through the utilization of Tsubame 2.5, which is faster, large-scale, and more accurate than the previous version.
An efficient and reliable CAE tool is very important for TOTO to design high-quality household products. We have developed an in-house code for complex multi-phase flows and ported it to GPU architecture. The code is well suited for large-scale computations on Tsubame supercomputer. we executed multi-phase fluid simulations of sanitary ware products with very high mesh resolutions on Tsubame. The simulation results agree very well with experiments. Now, the code is applied in designing various products, which substantially reduce the cost and accelerate the processes.
HPC is a key technology within the financial industry. To precisely evaluate financial risks, we use a lot of calculations to model a huge portfolio. This helps mitigate hidden risks which could appear and lead to economic loss. We use Tsubame to speed up risk calculations. We implement cutting-edge, large-scale financial simulations by running them on 1,500 cores. A large number of financial institutions in Japan are utilizing this technology.
In addition, Tsubame also plays a pivotal role in disseminating GPU computing in Japan. The Global Scientific Information and Computing Center conducts hands-on CUDA tutorials using Tsubame GPUs.
GSIC has been a host of programming contests for high school students by using our Tsubame supercomputer system every summer for more than 15 years. In this contest, we give one extremely hard problem, and student teams spend about a week to make a program for solving this problem on the Tsubame system. Their programs are evaluated on some test data set, and based on their correctness and speed, top 3 teams are selected and awarded at the last day of the contest. We spend a quite good effort for making interesting and hard problems based on current topics in various fields of science and technology. Like this example, the Tsubame system is and will be used to stimulate and encourage promising young scientists and engineers.
Tsubame 2.5, Tokyo Tech's next-generation supercomputer. Peak performance is 5.7 petaflops. Mixed scalar vector architecture based on the latest GPUs and CPUs. With tremendous memory and network bandwidth, real applications will execute with efficiency at unprecedented scales. Tsubame 2.5, also being the world's greenest supercomputer, is about to open new horizons into the future.